All right, now let's talk about our next set of special polar graphs, rose curves. These are called rose curves because they look a lot like flowers depending on how many petals you end up having. So rose curves will always be in the form where you'll have an a in front of either sine or cosine, and then you have some sort of number in front of the theta. Notice we're not adding or subtracting any value like we did in the previous ones, okay? So here's how you know how many petals you're going to have. If your n is even, you'll have an even number of petals. Wow. If n is odd, you'll have an odd number of petals. Amazing. This is where it gets weird though. If you have an even number of petals, you'll have twice as many petals as whatever n is. So if n is 6, probably should use an even number. If n is 6, we'll have 12 petals. That's not true for odd petals though. You'll have just exactly however many petals there are, or however many, you'll have n number of petals. There we go. So for instance, in this problem right here, since n is even, you're going to have 2 times 2 petals, or 4 petals. While on this one, since n is odd, on the cosine one, we're going to have 3 petals. Now, knowing how many petals you'll have is really helpful. That way we don't have to go as intense with like a reference graph. If we don't know how many petals there are, we're actually going to have to make a reference graph where we keep going until we get all the way out to 2 pi. Here's the problem. If you had like sine of 8 theta, remember to find your period, you're taking 2 pi divided by 8, so that's 1/4 of a pi. So we have to go 8 times, 8 cycles until we get to that 2 pi. That is obnoxious. Okay, so we're only going to use the reference graph, and actually I'm going to show you a trick so you don't have to use a reference graph, but I'm going to show you the reference graph at first. Really, I'm just going to use it right now to show you how to find your first petal, because once you know where one petal is, all the petals are equidistant from each other, and so you can just graph them from there. Okay, so once again, this is r, this is theta. I don't have to change anything, except I do know that my period is 2 pi over 2, because of the 2 right here. So our period is at pi. That means this will be pi over 2, this will be pi fourths, and this will be 3 pi fourths right there. So I'm just making a quick graph. So your starting point, or your starting petal, is just wherever you're going to hit the maximum first. Okay? It could actually be wherever you hit the maximum anywhere, but it's easiest to find where you hit it first. So sine starts at 0. The first time I hit my maximum is right here at pi fourths. So that tells me where my first petal will land. So the first petal will be out 4 units on pi fourths, so right here. So we're going from our pole, 0, and we're going out like so, and you get your first little petal right there. From there, since we have 4 petals, we just need to find, they just need to be equidistant, which on this problem you can go ahead and do visually, but sometimes it's a little hard to do it visually. So just as a quick trick, you can convert everything, or you can find how many, or how far apart, so the spacing between petals, by just taking 2 pi and dividing by the number of petals. Okay, so that gives me pi over 2. So every half pi, or if you like degrees better, 90 degrees, you're going to have another petal. Okay, so our next petal will be right here at 3 pi fourths, or 135 degrees. I don't care if you think about it in degrees, it's cool. Our next petal would be at 5 pi fourths, or 225 degrees. And then our last one will be here at 315 degrees. Voila. So there is your petal, or your rose curve with 4 petals. Amazing. So if I go to the cosine one, same idea. You can use a reference graph. We just need to figure out where our first maximum is. Here's the cool thing about cosine. The maximum is always going to be at 0. So yeah, I could figure out that this is 2 pi thirds and split it all up, but I'm just looking to figure out where my first pedal is. And it's going to be at 0. So I'm going to go out 5, 0. In fact, this is where I'm going to take a pause before we finish this. I want to take a moment to talk about where to start every time. If we're using cosine, you will always start at 0. And that's because we always start on the maximum. Now sine doesn't always start at the maximum. If we're doing like sine of theta, that's the maximum is going to be at pi over 2. If we do sine of 2 theta, it's at pi fourths. So you're always going to start at pi over 2 times the n, whatever the n is. So just as a quick little hint to find your starting point so you don't have to make a reference graph. The reference graph is helpful though if you need it. Okay, so we've got our first pedal over here in cosine. I'm going to draw from the pole. We've got our first pedal. I'm actually not drawing this totally correctly. I'll show you how it's supposed to look in a second, like how it's supposed to be drawn out. But we're going to start from there. So we got our first pedal right here. Each pedal should be equidistant, so you can do this in degrees or radians. So 2 pi, I'm going to divide my full circle 2 pi by the 3 pedals, and that doesn't simplify. But that's the same thing as 120 degrees if you want to change it to degrees. So I'm going to go ahead and go to 2 pi thirds, which is right here. I'm going to go out 5 because that's the length of my pedal. Because that's how high our maximum was. And then we'll go another 2 pi thirds, which would be at 4 pi thirds. We're at 240 degrees. There's our last pedal. Now when I said I'm not totally drawing it correctly, if you do it based on your reference graph, the graph would actually go like this. There's actually a specific order you'd graph it in. You'd go like this, then our next one right here, then right here, then right there, and then right here, and right there for the final end. In fact, if you want to see what this one would look like, so you'd go like so, all the way through. Just kind of like looping around. So this is the order it like goes in. So that's how it would look. So let's go do our last little pedal. It's called the single pedal. It's actually just another odd one. It's just a special odd one. And the reason we separate it is because when it's a single pedal, you're actually just drawing a circle. We do need to know where it starts. The length of the pedal is 2. Since it's sine, I showed you that little trick. Sine starts at pi over 2 times our n. In this case, our n is 1. So we start at pi over 2. We're going to go out 2 because the 2 in front right here. And then we're always go to our pole. I want you to notice that all of these graphs always do cross through the pole at some point. So this one's just going to be a little circle. And pretend that's a circle. And that's what that graph looks like.